Hi there, and welcome to the Hyperreal Quadruped Setup Training Workshop with ZIVA VFX. And this is where we get started with the awesome tool set, the ZIVA VFX software, which we're going to implement into our character setup. Now, before we get started with the character setup process using the ZIVA VFX software, let's take a look at what ZIVA VFX actually stands for and a quick overview of it. Okay, so this is the website where you can purchase or download non-commercial versions of the software toolset, which you can use for your animation, your rig exercise and practice. Okay, so if you take a look at it, you can find our product, the ZIVA VFX, from this link right here, and you can get a free trial to start up with the training process, or you could buy the software for production. All right, so if you just go through each of the their listing, you can see that their website provides a very intuitive way of representing how the software, how their tool set is going to be working, and how we're going to reproduce anatomically realistic character setup and creature rigs using this industry standard, industry leading tool set. Now, they have used this software in many of the big Hollywood blockbusters, as you can see, and the ZIVA tool set is continually getting more and more popularity, and it's getting adopted by many production houses and studios around the world. Okay, so there you have it. Just go through this website of theirs and take a look at their link, and now is a good time to get the software installed on your machine, because that's what we need to set up the rig. All right, now let's take a look at the documentation that they have provided. Now, the documentation that the ZIVA has provided to us is straightforward. It's more or less like an overview and introduction, and going over each and every of the menu items and the parameters and the technicalities of this tool set. Now, the documentation doesn't go over like building an actual character or actual creature or a quadruped in this case, but it does give you an insight of what this tool is all about, and the capabilities of the tool, and more importantly, the parameters and the algorithm and the tool set features, a quick summary and an overview. Now, please take your time with this. Okay, I highly recommend like taking a look at it and going through each of these documentation, because we will be implementing much of these setups in our character setup process, and some of the stuff that you may find confusing or having any questions, you can go through their documentation and take a look at it, and just go through the setup process. They have some pretty great resources out there, like building a virtual character, lion character, and like musculoskeletally based, anatomically physically accurate character there. So you can use that as a reference, as a guideline for the setup process as well. As for the introduction, you can see that the tool set is a physics-based animation, and why we use physics-based animation in a really short definition. Physics-based animation are the most accurate way of representing realistic bodily deformation. Right? So this is a physics-based, realistic, simulation-based setup, unlike the Maya muscle setup, which is real-time and which is based on deformation that is already built inside of Maya. The ZIVA VFX tool set just is a really, really cool and an awesome tool set to create physically accurate musculoskeletal system for our character rig and the production. And like I said, it's being adopted by many studios, and this is a really, really a big breakthrough, in other words. So you can go through these documentation, like why use the finite element method, some of these stuff that you have, like why do we go over physics-based animation rather than just sticking around with the traditional way. Those kind of things, just go through these. Okay, so they do have provided us with terminology, what these means, what's a solver, what's a creature node, what we have a body, simulation bodies, what's a bone, tissue, cloth, stuff like that, muscle fibers. Just go through all of these. Okay, they will take you, for the installation process of this tool set. They provided a really a nice step-by-step process of installing the tool set. They do provide you with beginner's tutorial stuff like creating a tissue system or a bone system, exploring different stuff. That's something that we will go over as well when building a character setup. Okay, but these are like the essential and the basic stuff, and the basic stuff is really what really matters. So please take a look at these documentation. They've also given some good practice and advice, like what kind of models should be used, so what kind of limitation do you have with the model, and the actual limitation of the tool set itself on creating the simulation and stuff like that. And we have some menus, like the overall overview of the menu system, the ZIVA toolset menu system, and different nodes that are associated with the toolset. Okay. Now that's pretty much it. So please, before we get started with this course, okay, make sure you install the software, and also make sure that you go through their documentation and try some experimentation, like creating a simple tissue system or bone system, creating attachment. That's pretty much it. That's all we need to get started with it. All right. Now let's take a look at the demo, the breakdown that we have for the hyperreal quadruped character using the ZIVA system. So let me just go ahead and play that. So you can see that the deformation that you're seeing with this result is fairly accurate and realistic. And the really cool thing is that it's the physics-based system, okay, and it's all simulation. So this is how it begins. So you have the model, you have all the rigs that you have created, okay, and you have a motion, the animation, that file that you have. Now everything runs from the bone. Okay, so this is the joint, the bone, on top of which we're going to attach the muscle system. And all of these muscle systems that we're going to build in this setup are polygonal models. And unlike the Maya muscle system, these models are custom modeled. So these are going to be modeled by the modelers. Similarly, on top of the ZIVA muscle system, we're going to add in the fascia system, which is like a thin layer of tissue on top of the actual muscle tissue, okay, muscle surface. So it's going to be creating, mimicking that surface sliding and wrinkling and stuff like that. On top of that, we have the fat system, the fat geometry, which is a thick layer of fat on top of the fascia system, which is going to create the result, the final deformation. On top of which we're going to add in the geometry, okay, the skin surface, that is, which is also will be going through some simulation process to add in more details. And you can already see that with this setup, see how the textures are lining up properly, like flowing properly. There's no texture distortion or stretching or stuff like that. You're seeing the nice muscle movement, good sliding going on the geometry and stuff like that. Okay, so please go through this demo, take a look at it, and it's going to be an overview of the process that we're going to be implementing on this workshop. Okay, so there you have it. That's the result that we're going to build. And I really highly encourage you to go ahead and push the boundaries, like add in more add-ons, more optics, play with the parameters, and come up with even better results. And that's what we would like to create in this workshop. So yeah, all the best, and let's get started with this. All right, so let's go to Maya, and this is what we have. And this is the scene file from our earlier lecture. This is actually the completed rig build for the character, and which includes the rig building and the skin cluster information as well. Now this is going to be your animation puppet rig. The animators are going to use this in the animation and the character animation process, and that animation is going to be integrated into the ZIVA VFX musculoskeletal system, where we're going to run some simulation and create a physically accurate, realistic character rig. Okay, so we do need character animation for the process to be implemented, because this is a simulation-based setup, and for that we do need to integrate the motion. Okay, so in other words, like integrating the motion. So this is the animation puppet rig, and you can see that it's fairly fast and intuitive way of controlling the rig. This, you can already see that this is the skin cluster information, and you can see the stretching and distortion on the skin, all that kind of thing. That's really not going to give you a realistic solution. In other words, if we take a look at that demo here, if you just go through, take a moment to look at the textures and the muscle movements and all these things, you can see that they're fairly staying intact. There's no distortion, no stretching, and no stuff. That's something that we were going to be that's going to be the output of the overall software and the simulation, and keeping the muscle system intact, and overall texture system intact as well. All right, so there you go. This is the rig file, and that's going to be provided to the animators for the animation. Now we're going to use this rig later on to add in the muscles and the skeletal system based on the ZIVA VFX system. Okay, now to get started, let me just go ahead and hide everything else. And first and foremost is, once you have installed the plugin, you will need to load it from the plugin manager, and you can see that it's somewhere in there. So there you have it, loaded, auto loaded. Okay, now once loaded, you will now see that you have the ZIVA menu set and the ZIVA tools menu set. Okay, now if you take a look at the about section, you can see that this is version 1, where they have completed and worked on a final iteration of the fascia, or these cloth skin system implemented. Okay, and also make sure that you're using the version 1 or above, because there are some really useful add-ons that we need to create the rig in a more robust way, such as muscle line of action stuff, and also a complete iteration of the cloth system. Okay, and that's pretty much it. So the other thing that we're going to be using are, like, if you take a look at it, there is this combined system, the muscle bone combined system, which is also available with the version 1, the G poly combined tool set, and also creating line of action curves. These stuff are something that we're going to be using in the process. Okay, now at the beginning this might look a little we're quite unfamiliar with this, like a new tool set, new stuff, but please, like I said, take a look at the documentation that is provided and go through that menu set feature, and going through all the stuff that we have, you can easily learn the basic and understand the menu and the layout. Okay, now let's go over this. Now with the ZIVA toolset, it is primarily being controlled by the solver. Now it's similar to what we have with the nucleus node or the enclosed system, the inbuilt Maya dynamic system. Okay, so solver controls everything in it. Okay, and then we have the simulation components, such as the tissue system, which is going to be our muscle stuff. Okay, and then we have the cloth, that is the fascia system or the skin simulation system. We have the bone. Obviously bones are going to be non-deformable stuff, where we're going to attach stuff, but also they will play an important role in giving us a proper collision and sliding. We have attachment node, which we're going to use to attach tissues to bone, or bones to tissues, clothes to tissues, and stuff like that. Okay, and then we have goal attachment. Primarily we will be using the tissue properties as well, which includes like layering the materials. Now each of these tissues has their own unique identity, a unique material. With these materials you can make the tissue very soft, like maybe a brain tissue, maybe very rigid like a scar, stuff like that. It's all based on the parameters that we're going to play around. Okay, similarly we have muscle fiber. This is another very interesting topic that we need to be implementing into our rig system, which is going to give you that nice ability to trigger and relax and contract the muscle, and creating the muscle excitation that is needed for realistic setup. Now muscle line of action works together with muscle fiber and every other parameters that we have to create a auto fire system, automated excitation of the muscle. Now this can be a little technical, but we're going to go over that, all over that in the future. Okay, so obviously we have the collision mesh, soft tissues, embedded buses, and user tape mesh. And similarly, we can put in cast. We will be using this function a lot because simulation obviously takes a lot of time and effort. So obviously we need this functionality to adding cast, clearing, saving, and loading cast. Okay. And other than that, we have ZIVA toolset, which we're going to use. Like they have some runtime demo of Anatomical Arm, some source for template files that they already provide with you. They have some missing information like G polycombine. This is a much better option than using the polycombine feature that Maya has built in. We'll be using that later on. We have some run mesh analysis, which is going to be used to analyze the mesh that we have and make sure that the mesh is all set and ready to be implemented inside the ZIVA toolset. So making sure that the vertex and faces and stuff like it matches the pipeline for ZIVA VFX system. Okay, so we can additionally select tissues by just clicking on these buttons, and that's pretty much it. Okay, that's all there is. So not much. Most of the work, you know, it's going to be artistic and technical, and we'll be using all of these tool set together. Now, just wanted to let you know that ZIVA toolset is really, you know, I would say like a user-friendly tool set, and it really speeds up the workflow that you're implementing. So once you get an idea of this, once you get a grasp of this, and you have a robust machine at the same time, you're gonna come up with like creating realistic creature character simulation in a very small amount of time with a very little workload and in other words, very little manpower. That's all it needed. It's pretty robust. Okay, so let's take a look at some of the demo they have, like the anatomical arm. So you can go ahead and create that and take a look at it, and you will automatically get an idea of how this system actually works. So you see this is the bone here that they have created, and these bones. Now these representation of the in the viewport that you can see, we'll go over that in a little while, but let's take a look at it. This is the muscle. Okay, these are the tissue system. That's the tissue build. Then we have the bone. All right, and then we have the geometry itself, and you can see it's being controlled by this rig here. All right, now for this to work, we need interactive playback or simulation running out. This is not real-time solution, so it's not going to work for us. So for this, you will need to go to ZIVA toolset and make sure interactive playback is turned on, or you can additionally create a self icon that I've done here. Click on interactive playback, and you can see that it runs through the simulation and go through the result that you're seeing there. So you can see how the muscle behaves, how everything follows along, and looks pretty cool. Now this may be a little slow and sluggish. This is because if you take a look at the G solver, maybe the collision detection is turned on. This really slows the machine. So make sure when you're trying it out, you're testing it out, you just disable the collision detection. Now this is what I meant by the solver. This is the G solver node, which you can see represented by this little locator, in other words. And this also represents the scale of the model. So you can see the scale is controlled by the scale. You can increase or decrease by just scaling it. And this scale is physically accurate. So if you have a character that is standing 1 meter tall, you better make sure that the solver is accurate at 1 meter. And that's going to give you the best optimum result that you're looking for. And this is again a very important parameter that you need to check, like the scale parameter. Okay, and this is the start frame where the simulation gets started. It's at the frame number 1. You can see these are the parameters for controlling. You can control, disable the collision, the iteration, and sub-step, just like any cloth system. It is the frame per second. At this moment, it's running at 24 FPS. So that's the setting here. This is the gravity, the stiffness, and those kind of things. All right, so let's take a look at the simulation. I've disabled the collision system. Let's take a look at the play, the interactive play. And you can see that already it's a lot faster, and see how the simulation running along. It's going to give you a really nice result. So you see how the muscles are attached to the bone and always following the movement, at the same time giving you that nice muscle fiber stuff, the movement that's going on. All right, so I'm just going to delete these keys, and let's take it. Let's see the result. There you go. So you can see that. There you have it. It's pretty good. right? Definitely going to give you the tissue system. So again, the really cool thing about Jiva's tissue system is that it gives you the ability to control the muscle parameter. Like if you want it to be really stiff or really loose, you can control that. So all you need to do is just select the muscle object, and you will notice that in this muscle object, there are a couple of nodes that's controlling it. One of them is G material, and this is the material node which is going to make the model either very stiff or very loose. So it's going to determine if your model is like a brain tissue or maybe some other muscle tissue, could be like a scar. All you need to do is just change the Young's model that you're going to control. So the more stiffer it is, like for example, I'm going to put it 10 to the power 10 and see the result here. And you see that immediately it's much more stiffer. See? Right? It's a lot difficult to articulate the hands as well, because this is a really stiff muscle. Right? So in a similar manner, if I'm just going to change that muscle stuff to 10 to the power of 1. Okay, so this is going to give you a very soft tissue like this. There you have it. All right, so let me just delete the keys so it's more interactive. And this is the result that we're getting. And the really cool thing is that with these materials, you can layer the materials on top. So if you want only this stuff having like very soft feel, like a less stiffness, and you want the rest of the muscle to be very high stiffness, that can be done. And that's exactly how the organic muscle and the tissue system work. And like I said, that's all that's integrated inside of the system. Okay, so there's an example. This is a quick example that I wanted to show you. Please go through and play with it and see the result. Okay, now what I'm going to do is basically go ahead and experiment by creating our own very own muscle system. Okay, so let's get started with this. So I'm just going to go ahead and create a polygon sphere. And let's increase the resolution on this so that it's fairly dense, and we have good tessellation and resolution for it to play around. There you go. That's pretty much it. Let's delete that. And I'm going to create a polygonal cube as well. There you go. So in this case, what we're going to do is we're going to have the cube to be the bone object and the geometry, the sphere, to be the tissue system. Okay, the muscle system. So in order for this to work, what we need to do here is select the bone geometry. All you need to do is either create a solver or simply selecting the surface, click on bone. Now this automatically creates a solver system for you, which is going to be uniform and unique for the entire muscle system that you're going to build on this this scene file. Okay, so you can immediately see that when you created the bone, it automatically creates the solver, and then you have these the geometry, the bone parameter. So you can easily see that it's tessellated. And if you take a look at the channel box, it went ahead and created a new attribute called G bone. Okay, so if you take a look at the G bone attribute, it gives you a couple of attributes like functions like collision, collision volume, and the stiffness. And again, it has this stiffness factor. You can increase or decrease that based on this value. Now, immediately after creating the muscle, you may want to scale the solver, because you can see that our model is fairly small. So let me just go ahead and scale that. And this is going to represent a 1 meter scale. Okay, so how big do you want? So for example, I want this to be the representation of 1 meter, and it's about, let's say, 2 in the scale factor. There you go. Now if I hit interactive playback, you'll notice that nothing happens because bone is not affected. So for this to work, we will need to make sure that the sphere has a tissue system on it. So I'm just going to click on tissue. There you have it. So immediately once you've created the tissue, you will notice that there is a new representation of the geometry, and the outer, this weird stuff that you're seeing here, this is what we call the Z-tip. Okay, so this determines the tessellation, or the amount of tessellation, the the software is going to simulate, that is going to be reflected on the muscle system. So you can increase or decrease the resolution from the step size. So if you want, you can go ahead and reduce that, like for example about 0.2, and that gives you a higher resolution. If you want to increase that, you can have a much higher value, which is going to look like that. So you can see the result. We're going to take a look at it. All right, now let's hit interactive playback, and you see that immediately the material, the tissue, is going to fall under the influence of gravity. This is because if you take a look at the G material, the solver node, we already have set the gravity to a value of -9.8. That's the Earth's gravity, meters per second, right? So if I disable that, it doesn't have any effect of the gravity. Maybe it's in the space, no problem. So let's put it at a value of -9.8. That's the gravity factor. And the next thing that we want is we don't want the tissue system to be falling, to the infinity. So what we're going to do is just attach that to the bone. All right. So to do that, you need to select the vertices for the tissue system. I'm just going to select these vertices here. Shift select the bone geometry. Make sure you're holding shift and selecting the bone, and click on ZIVA attachment. Click on attachment, and you can immediately see that those vertex now has a connection to the tissue system, the bone system. And immediately when you hit play, interactive playback, you see this result here. I'm just going to increase the time slider, and you can see that now I can interactively play this. This is going to give you this kind of result. There you have it. So it's so much faster and so much robust, as you can see. Right now, let's play around with these values. Let's go to the sphere and change the resolution of the TET size. So I'm not quite happy with the resolution. You can see that it's fairly blocky, right? But with the increase, with the higher value of the TET size, the simulation is going to be obviously much faster, but not physically accurate, not realistic. So you just need to change it to the parameter that you want it to be fairly physically accurate. So if you want, you can reduce the TET size to a lot smaller value, and this is going to increase the amount of resolution, as you can see, right? And this is going to give you more complex, more detail on deformation. So if I hit interactive playback, obviously you can see that the result, the simulation is a lot slower, but it's starting to get some nice detail in the shape. There you have it. Now I don't want this to be so slow, right? So I'm just going to increase the TET resolution to about 0.3. Fairly good enough, and see the result here. And you can immediately see that this is the kind of result that we have. We have a very nice, soft tissue material system that's going on in here. Now, if you want, you can go ahead and increase the stiffness by going to the Young's model and changing that to a higher value, maybe 10 to the power 8. And hit interactive playback and see the result, and you can see that it's very stiff now. It's like like a punching bag or something like that. So if you want, I would like to change that to a very soft parameter. Let's set 10 to the power of 3, interactive playback, and this gives you a much better result. You know what, I'm going to change this to about 10 to the power of 5. Okay, there you go. That's much better. So you can already see the result. Now the other thing that we need to notice here is that when you change this setting, there's also some other factors that's determining the way that this geometry is going to simulate, and that is the positions ratio and also the Young's model factor. So you can increase this value. This is going to be connected to the Young's model factor as well that we have. They're both going to work together to give you the amount of stiffness that you want. This is also going to control the ratio. If you take a look at it, just do a quick Google search or internet search and see what you find with the positions ratio. It's basically a factor that determines the tissue. Okay, so how it's going to be simulated, how how the physical behavior of the material, those kind of things. So please go through that. The other important thing is the volume conservation or volume preservation, in other words. So if you want, you can set it to a full value of 1, and again it's controlled by this factor. The more you have, the more the volume will be preserved. Okay, so it's basically something that it's going to determine the volume. And again, for geometries, the organic geometries, at least we want the volume to be preserved, right? So let's go ahead and change some of the settings here. Take a look at some of the settings that we have here. I'm just going to put it to a value of 0.3. And let's take a look at the attachment node. So the bright reddish attachment node that you have. And again, it's going to be controlled by the stiffness factor and the exponential factor that we have with the stiffness, which can be determined by these values. The less the stiffness you have, for example, let's say 10 to the power of 1, the less stiff it is going to be. So it's going to be falling until and unless it's going to retract back, but not going to happen because the gravity is too strong for the attachment. Okay, so you can go ahead and play with this value as well, like let's say about 10 to the power of 5. Interactive playback. You can see that the attachment falls. It's behaving more like elastic stuff now. It's going to go down and, you know, like a rubber band, right? So see how accurate it is, see how interactive it is. I'm just going to change to 10 to the power of 8. That makes it much more stiffer. Now you can change the attachment type mode from fixed to sliding. Now many times you might want to change the type of sliding, a type of stiffness that you want from the geometry. Most of the time it will be fixed, but sometimes we do need sliding as well. So when you change it to sliding, the color changes to purple, and this is going to give you the sliding parameter. So you can see that how the muscle is going to slide along this geometry, like so. That's pretty cool. So you can see how this is going to give you a real-time result of the simulation. So that's going to give you the sliding. Again, it's being controlled by the stiffness. The less you have, the less stiffer it is going to be. I'm going to change it to fixed again. And let's take a look at it, how it's going to look like. And that's pretty good. All right. So let's change the material behavior of this geometry that we have, this tissue we have. At this moment, I want it to be really stiff. Okay, so at 10 to the power of 5, this is what it looks like. But like any other muscle or a tissue system, I want to be fairly accurate, and I'm building this tissue where the upper, certain portion of the tissue is really stiff and a certain portion of the tissue is really soft. So this is where you can layer materials. Okay, so in this case, I'm just going to select the geometry, go to ZIVA, and add in a muscle layer. Okay, so that's going to be material layer. Just click on that, and it's going to add a new material layer for you. Okay, and you can see that we now have material 1. This is the start. This is the first. This is the original material, in other words, and this is the new material that we have created. So you can control these material factors. So I'm just going to make sure that the G material 2 is about value 2, or I'm just going to name it like, it's a lot easier that way. This is going to be soft. It's going to be hard. There you go. So you now have a new material, and if you're going to interactive playback, you'll see that everything comes along, everything works together. I'm not quite seeing the result that we want. So this is where we can go ahead and paint the width. So if I go to paint, you can paint the width for the G material for the soft or the hard width. Okay, so here I want the hardness to be all over the geometry, and I want the softness. Let's go to the paint. Where is that? And I'm going to double click on that. It's going to open up the artisan tool set. I'm going to zero that out. I'm going to put this softness only at the bottom, somewhere around there. Maybe you can flood it out, okay, to create a much softer look. And if you're now going to play it, just go ahead and you see the result. So it's a lot stiffer, a lot less stiffer at that end where we have painted the width. I'm going to be a little more creative with this. Okay, I'm just going to paint this out and let's give it a blocky portion here. So let's say this is the character's stomach. Okay. All right, so you can see that this is the reason where we have painted the material, soft material width. And if I'm going to interactively play that, you see the result? There you go. So it's a lot stiffer at that end and a lot harder at the other end. So there you go. There's the result. Now you can go ahead and custom tune the parameter that you want. Maybe for the hard, I want it to be 10 to the power of 4. For the softness, about 10 to the power of 3. And you see the result. this is what it's going to look like. So that's material layering. So you can add as many material layering as you want. Obviously, the more layer you have, the more complex the system gets. Okay. Now the next thing that we're going to take a look at is the excitation. Okay. So in other words, the muscle relaxing and contracting, the triggering factor, which is going to be determined by putting a new tissue property, that is the muscle fiber. Now this is basically just the tissue stuff. Okay, this is basically just the tissue stuff that is going on with a predefined material system that we can play with. But with this geometry, if you want to create a muscle system, okay, a realistic muscle, you will need to go ahead and convert that, or add a new property to the tissue, and that is the muscle fiber. And that gives you the ability. Now you can see how if I go ahead and just select, there you go, that's the muscle fiber, that's the color red, and it's going to determine the factor for the muscle. So you can, again, it has the strength, how much strength you want for the muscle fiber, and then you have the strength exponential, which you can increase or decrease depending on the necessity. And then you have excitation, the muscle fiber excitation. So remember, when you have a character like working out and just curls a bicep, like holding a dumbbell and start to curl, and it's really a very heavy piece of dumbbell, and that's where the muscle fiber comes into play, where you need the excitation and the relaxation of the muscle to simulate realistic muscular behavior. Okay, so for instance, if I go ahead and interactive playback this and I turn on the excitation, you see how this, like, zero it out, it's going to relax the muscle. When I turn it on, it's going to be full value of 1, and you can immediately see that it's actually being represented by the color change in the color. So the red means a relaxing muscle, okay? Then you have the excitation with the yellow. If I'm going to blend it slowly, it's going to change the color excitation in a similar manner as well. Okay, and again, you can paint the way the excitation work as well. Like if I just go ahead and select the geometry and paint with a G fiber, so you can determine the width and the end point as well, where the muscle excitation is going to be located, or determining the direction of the excitation. You can do that, but by default it's already set, so it looks pretty good. Okay, the next thing that we want here is to trigger the excitation. Like we already have the G fiber, that is the muscle fiber stuff, but how do we trigger the excitation? That's what we need, and this is where the new tool set, that is the create line of action curve, comes into action. Okay, comes into action. Yeah. So what we're going to do is just basically select the geometry, and this line of action tool set, what it does is determine the length of it creates a curve, and that curve is going to have the length equal to the length of the sphere, okay, or the muscle object that you have, and based on the length of the curve, it's going to trigger the excitation and relaxation of the muscle. Okay, so all you need to do is just select the tissue, and I'm going to go to the create line of action curve, and you can immediately see that it created a curve here. I'm just going to isolate that, move it aside, and you can see it has the exact length of, in other words, a diameter of the tissue. Okay, now all we need to do here is connect this stuff with the muscle system, because what we're going to do here is this has a point which we can increase or decrease the length, and that's going to determine the excitation factor. Okay, so let me just go ahead and select the muscle fiber. There you go, select the curve. Okay, first of all you need to select the muscle fiber, then select the curve. Okay, go to ZIVA and click on muscle line of action. There you have it. So you can already see now that it has made some connection with the G line of action, and it has some max excitation, some attributes that you can play around later on to fine-tune the kind of deformation, the amount of deformation that you want for the muscle excitation. But let's see the result. You see that by moving the vertex, it gives you the result, right? So what we need here is the change in the component position to trigger the excitation. There you have it. This looks pretty good. In other words, what I'm going to do is just select this curve and and create a cluster on that. That's a lot easier. Okay, and I'm also going to represent the muscle and change in the color. Okay, so let's go ahead and select that, and let's trigger the muscle, and you can immediately see that there you have it. We are triggering the muscle fiber excitation, and it's being triggered by this line of action curve. Very intuitive. And remember, this is all going to really be implemented into the setup that we're going to have in our character later on in this course, and it all will start to make sense. Okay, there you have it. That's the muscle excitation. Okay, so if you wanted, you can also control the muscle excitation custom or manually. If you want to key that and animate, no problem. You can do that by going to the excitation parameter, that is the attribute, and playing with it. Okay, so that's something that I've always shown you. There you go. So if you want, you can have the animators play with it or key with it. You can go ahead and trigger it based on the look and feel that you want on the character. So that controls the muscle fiber excitation, or in other words, you can call it auto fire triggering. Okay, and that's pretty much it. Now the next important aspect of this setup is the collision, right? So for the collision, let me just go ahead and create a new polygonal mesh, and let's create a cube, and there you have it. So this is going to be a new bone for us. So let's go ahead and create a bone. There you go. And again, it's going to be driven by the same solver system here. And if I'm going to interactive playback that, you can see that it's basically going underneath it. Not much to do here, right? But what we can do here is turn on the collision detection. And this is going to help us with the detection of the collision. And there you have it. All right, so see how accurate it is. And it also has this sticky nature with the colliding surface, typical of a tissue system, right? And now with this collision, you can play with the amount of, you can play with the collision point spacing, which is going to give you a much better result. Iteration, like spacing of each and every of these collision points, stepping it up with the sub-step or iteration, and getting a much more better result. Now the ZIVA system, the ZIVA VFX system, also includes the addition of, if you take a look at the attribute editor, there's something called G tissue, okay, node, which is unique to each of the tissue system that we have built. Okay, so the tissue system that we have, the G tissue system, it gives you some additional control about the stiffness factor, and also enabling and disabling collisions and self collision. All right. Now, if you don't want any collision to be taking place, you can just disable that and hit interactive playback, and it's not going to collide whatsoever, right? But if you're going to interactively have the collision system working, you can turn it on, and that's going to give you the collision. There you have it. And in a similar manner, if we can have the self collision turn on, and that way the tissue system itself will be colliding. Okay. And obviously this is going to be a lot more memory and CPU intensive, but if you want that amount or level of detail, that can be done by simply turning on the self collision. And you can see that it also has this factor of contact sliding, where the geometry, when it comes in contact with bone object, is going to create a sliding effect. Or if you don't want that, you can disable that as well. All right, so those are some of the features and a quick overview and an introduction that I would like to go over with the ZIVA VFX awesome tool set, and that's something that we will be implementing and using throughout this course. So these are the basics, okay? Like I said, introduction and taking a look at the documentation that they have provided is the crucial, is very crucial and very important to learn the medium and the software. So please go through that. Make sure the tool set is installed, okay? And for this workshop, this class, you can just go ahead and play with the tissue system, create your own tissue, and play with different parameters, attachments, and bone systems, and generally just learn the basic of implementing the tissue system, which is built inside of the ZIVA toolset. Okay, so if you run into any confusion, any questions, please feel free to ask, all right, and I will be more than happy to answer them. And in the next lecture, we're going to start sculpting and creating the muscle bone stuff, all right, and to implementing this system into our rig build. So that's pretty much it, and thank you for your time, and I'll see you soon in the next one. Bye bye.